Hello, grade 11s. We're starting our final unit in chemistry today. We're going to be starting organic chemistry. So organic chemistry is the chemistry of carbon. Organic carbon compounds are any compound that contains carbon atoms. Quite often you're going to find hydrogens or oxygens as well, but you're always going to have, at the very least, carbon. So we're going to want to remember that if we see carbon, we're dealing with an organic compound. Now, the thing about carbon is that it always has 4 valence electrons. It's in group 4 on the periodic table and has 4 valence electrons, which means it's capable of making 4 bonds. I really want you guys to remember the number 4. It is really important that you do that because one of the most common mistakes kids make when drawing organic compounds is they forget to count to 4. Take a look at the examples that I have below. In the case of methane, you can see that the carbon is bonded to 1, 2, 3, 4 hydrogens. In ethane, this carbon is bounded to 3 hydrogens and another carbon. This carbon is bounded to this carbon plus 1, 2, 3 more hydrogens. Each of these carbons has made 4 bonds. Even in this case of ethene, we still see 4 bonds, each indicated by a line, because the carbons are double bonded, so 1, 2, 3, 4. And it is possible for carbons to form double and even triple bonds. The other thing that is really important is that carbon can form bonds to itself indefinitely. We can have one carbon attached to another, and that can go on and on and on forever. And so carbon's capable of forming all kinds of different compounds. That ability is called catenation. So catenation is the ability to bond with yourself over and over again, and carbon does that. Now, there are so many different types of organic molecules that we have developed our own naming system, our own nomenclature for it. So we're going to start following down along this side of the line. We want to remember that all organic compounds are compounds that contain carbons. As long as they contain carbons, they're going to be organic. We're going to start by looking at hydrocarbons. Hydrocarbons are compounds that contain carbon and hydrogen only. There will be no other atoms involved in any of the bonds. Now, in the hydrocarbons, there's 2 different main groupings. There are the alphatics, which are the carbon-hydrogen compounds that form straight chains. And I put the word straight in quotes because in reality they're not exactly straight lines, but you will see long chains being formed in the alphatics. The aromatics form special kind of ring structures, which we will come back to. Now, in the alphatics, there are 3 subgroups: alkanes, alkenes, and alkynes. These 3 subgroupings are based on the kind of bonds that they can form. Today we're going to start with the alkanes. Alkanes are any hydrocarbon, so it's got carbon and hydrogen only, that has only single bonds between the carbon molecules. All other bonds then are made up with by filling in hydrogens. So take a look at these 2 examples. In this first example with the orange carbons, which I'll just kind of highlight over here in blue, you'll notice that there are single bonds between each of the carbons. There are single bonds on either side. All the remaining bonds would be filled up with hydrogens. There'd be a hydrogen here, and here, and here. All the way around, we'll have hydrogens taking up the remaining spaces. The name, however, is based only on the carbon chain. So very often, you'll see me draw my structure showing only the carbon chain so that I understand how the name will be. Anytime that we have a compound with all single bonds, we call it saturated. What is it saturated with? Well, it's saturated with hydrogens. Saturated means that the hydrocarbon has as many hydrogen atoms as is possible. So it's saturated with hydrogen atoms. And these chains can go on forever. You can have a 1-carbon alkane, a 2, a 3, a 3 million. They go on for incredible lengths. So we definitely need to have a special naming system. So our naming system starts by finding the longest chain that you can find without lifting your pen from the page or backing up on yourself. We have special prefixes that describe how long your longest chain is. Chains that are 1 carbon long start with the prefix meth. Meth means you have a 1 carbon chain. All alkanes end in -ane. So meth means you've got a 1 carbon chain, and the only bond length you'll see is a single bond. A 2 carbon chain starts with F. F means you have 2 carbons. Again, the ending -ane means all the bonds that you will find will be single bonds. Prop means 3 carbons, so propane is a 3 carbon chain that has all single bonds. You can see an example of that here. The large picture that I have down at the bottom is also propane. You can see how the molecule is a little bit bent, but the bonds between the carbons are all single bonds, so it is an alkane. Because it has 3 carbon atoms in the longest chain that I can draw, it is propane. The number for 4 is bute. Butane is a 4 carbon chain. The other numberings, up from 5 up to 10, are prefixes that are more familiar to you. The symbol for 5 is pent, the prefix for 6 hex. For 7 we use hept. Even though sept is common, we use hept. So heptane is a 7 carbon alkane. 8 is oct, 9 is non, and 10 is det. We always find the parent chain by finding the longest chain of carbons that I can find and then naming it based on the number of carbons. One of the most useful tools you're going to find when doing any kind of organic chemistry, whether it's here in high school or when you're going to university, is to pick up a highlighter. They really make your life a lot simpler. Highlighters are wonderful ways to find the longest continuous chain. So we're going to do that. Now this first one is reasonably straightforward. The carbons are all in a line. So the longest chain of carbons I can find has 1, 2, 3, 4, 5, 6 carbons in a straight line. We name this molecule hexane. Hex because it has 6 carbons, and ane because they're all in single bonds. But it doesn't matter whether or not we change direction as we draw the line. We can bend our molecules as many times as we need to. This molecule also has 1, 2, 3, 4, 5, 6. At no point did I lift my pen from the paper. As I continued all the way through, you will notice that I kept my pen down, I didn't back up on myself. Organic molecules can bend and fold just like pieces of paper. So this one is also hexane, just as this one is hexane. They are the same molecule, one is just bent. What about our third choice? In this case, I have 1, 2, 3, 4, 5. I have a choice to make. I can go 6 and go this way, or 5, 6 and go this way. It really doesn't matter. In both cases, again, we have found a 6 carbon chain. But this hexane is different because we now have this branch sticking off, and we have to know how to name it as well. Any carbons that are not part of the parent chain are called a branch. We have to find a way to name the branch. It needs not only a name, but also we need to have a way of saying where did it branch off of the chain. Branches are also called radical groups. They end in YL but use the exact same prefix system that we used with the alkane parent names. So a 1 carbon long branch is named methyl. Meth for 1 carbon, YL telling us that it is a branch. In organic chemistry, every syllable has a meaning, and that's a helpful way for us to remember it. A carbon branch that was 2 carbons long would be F. And again, YL tells us that it's a branch. If it was 3 carbons long, propyl, and 4 would be butyl. Take a look at these 2 examples. In this first one, again, you're going to notice that the carbon chain is 6 carbons long. A 6 carbon chain is called hexane. But sticking off of the hexane chain is a branch. This carbon is not highlighted. The branch itself is only 1 carbon long off the main chain and is called methyl. Meth, because it's 1 carbon long, YL, because it's a branch. Just as with our parent chain, hex, because it was 6 carbons long, and ane, because they were all single bonds. In the example below, we again have a 6 carbon chain. Again, my parent chain is hexane. We have hex because it is 6 carbons long, and ane because it's all single bonds. But this time the branch that is sticking off is 2 carbons long. This is 1 single branch because it comes off of the parent chain at only 1 spot. But it is a 2 carbon long chain. We name it ethyl. F because it's 2 carbons long, YL because there's a branch. We also need to say where these branches live on the parent chain. So we do this by numbering each of the carbons in the parent chain. Both of these are 6 carbon chains. It doesn't matter if you number from the left or the right. What does matter is that you number so that you give the lowest possible numbering. If there's only 1 radical, that gets the lowest numbering. If there's more than 1 branch, then we need to find the lowest possible combination of numbers. So, in this first example, I chose to number from left to right. This puts my carbon branch, my methyl branch, on carbon 3. Had I tried to number in the opposite direction and call this carbon 1, 2, 3, 4, 5, and 6, that would have had my carbon coming off of carbon 4. Carbon 4 is a higher number than carbon 3, so that would not be lowest numbering. Again, we always want to have the lowest possible numbering. So on carbon 3 of my parent chain, there is a methyl branch. It is the same with the second example. Again, I could number from left to right or starting at the bottom. But this is the direction that gives the lowest possible numbering. We always want to give the branches the lowest possible number. Let's put this all together now. When I go to name these things, it is important for us to remember that organic names are all one word. Hyphens are used to separate numbers from words. So we don't ever want to have a number and a letter side by side. They don't like each other in chemistry. So to separate them, we're going to use a hyphen or a dash. If we have to have more than 1 number side by side, then we're going to use a comma to separate them. If I have more than 1 branch, you've got a choice. You can either name them all in alphabetical order, so your ethyls would be named before your methyls, regardless of where they show up on the chain, because E comes before M in the alphabet. Or you can choose complexity order. Complexity order says name the shortest to the longest. So your methyl will then be named before your ethyl because it's a shorter to the longest. Again, what you're not allowed to choose as a direction of naming more than one branch is the order you see them in. It's either alphabetical or complexity. So putting this all together, on my hexane chain, I have a methyl branch, and that methyl branch is on carbon 3. 3-methylhexane. In the next example, on my hexane chain, on my 6-carbon chain that we highlighted earlier, I have an ethyl branch. It's a 2-carbon long branch, and I can find it on carbon 3 of the hexane chain. It is 3-ethylhexane. So we're always going to find ourselves working somewhat backwards when we name organic molecules. Let's go through these two examples together and name them. In the first example, we're going to start by finding my parent chain. My parent chain has 1, 2, 3, 4, 5, 6, 7 carbons. The prefix for 7 is hept. Because all the bonds in between the carbons are single bonds, it will end in ane. My parent chain is called heptane. Now, after I've highlighted the longest chain I could find, I notice that there is a branch sticking off. My branch is only 1 carbon long. It is a methyl branch. Meth, because it is a 1 carbon long branch, YL lets us know that it is a branch, methylheptane. Where does methyl live on heptane? In this case, the numbering works best if we go from right to left. This puts my methyl branch on carbon 1, 2, 3 of the 7-carbon chain. So 3, remembering a dash because letters and numbers don't like each other. The name for this molecule is 3-methylheptane. In our next example, again, finding the longest continuous chain of carbons I can find, 1, 2, 3, 4, 5, 6, 7, 8. I can find an 8-carbon chain. Now I could have bent that down at the end, and that's fine as long as we get to 8 is the longest you can make. There are 2 branches. There is a branch coming off here and a branch coming off here. An 8-carbon chain is called octane. Oct for 8 carbons, ane because single bonds. We have 2 branches. This is a 1-carbon branch named methyl. Meth because it's 1 carbon long, YL because it's a branch. This one is also called a methyl. When we have 2 of the same, these are 2 separate branches that come off at separate locations, we can use the prefix di. Di means that we're going to have 2 of the same. We now need to be able to say where all these branches live, so we're going to number my parent chain. Again, we can quickly see that numbering in this direction will give the lowest numbering. Carbon 1, 2, 3, 4, 5, 6, 7, 8. We have branches coming off at carbons 2 and carbon 4. So let's put all of this together. Starting at the end and working my way forward, we're going to have octane being my parent name. On octane, we have methyl branches. Meth, YL for methyl. There are 2 of the same, so I'm going to use the prefix di, dimethyl. And every branch gets a number. Even if they're on the same carbon, they get a number. Because there's 2 separate branches, we need 2 numbers. One of them will be on carbon 2. The other one will be on carbon 4. We now need to remember a dash between a number and a letter. This is 2,4-dimethyl octane. How do we go in the other direction, though? If I give you a name, how do you draw it? Suppose I give you a really simple name, like 2-methyl propane. This is a good example for us to follow. How do I go about drawing this structure? I always start by breaking down the name. As I break down the name, I notice at the end, starting at the end first, propane. Prop means that I'm going to need 3 carbons, and ane means the bonds between them will all be single bonds. So 3 carbons with all single bonds. Continuing to move forward, meth means that I need a 1 carbon branch, and I know it's a branch because of the YL. The number 2 tells us where the branch lives. This 1 carbon long branch will live at number 2 on my propane chain. Regardless of the style that you draw, we always start with a skeleton. The skeleton is just the carbons and no hydrogens. So 3 carbons in a row is propane. Adding the methyl branch to carbon 2 is methyl. This is the skeleton for 2-methyl propane. Structural and condensed are 2 ways of adding the hydrogens on to complete the 4 bonds that all carbons must have. Regardless of whether you're asked to draw a skeleton, a structural, or a condensed, you always start by drawing your skeleton. When we do structural, we're actually going to draw a bond for each hydrogen. This first carbon has 1 bond already. We can see that it will need 3 more bonds to hit that magic number of 4. All carbons must have 4 bonds. This carbon in the center already has bonds in 3 spots to other carbons. It only needs 1 more bond to make up its 4th to get to 4 bonds per carbon. This carbon as well will need 3 hydrogens to make a total of 1, 2, 3, 4 bonds. And the one on top also will need 3 hydrogens. Drawing structural diagrams takes up a lot of space on your page, which is why we also draw condensed. Condensed or condensed structural are ways of drawing the same molecule but without taking up so much space. In a condensed structure, also called condensed structural, we merely say how many of each hydrogens there are. This first carbon has 3 hydrogens, as does the top one and the end one. This central carbon that we have here has already got 3 bonds. It only needed 1 more, so I'm just going to go CH. I wouldn't write CH1. We always assume the number 1 in chemistry. It's important that you remember to put a capital letter H, because capital H is the correct symbol for hydrogen. I'm going to get you guys to practice drawing skeletal, structural, and condensed for all of our alkanes. There is one more kind of alkane structure we can draw, and that's a cycloalkane. The word cyclo means circle. These structures form rings, but they still will all have single bonds because they end in ane. We're going to follow the same set of rules. Let's try drawing cyclopropane together. I know that I'm going to have cyclo, meaning my parent chain will form a ring. The word prop means that I'm going to have 3 carbons in that ring, and the word ane means that all the bonds will be single bonds. So to put 3 carbons in a ring with single bonds, we actually get more of a triangle shape. This is the skeleton for cyclopropane. In this case, I'm going to do a structural formula, just to practice. This first carbon at the top has already got 2 bonds coming off of it. It will require 2 more hydrogens to get to 4 bonds. This second carbon also has two bonds coming off of it. It also needs two hydrogens. Same with this last carbon. This is cyclopropane as a structural formula. I'm going to do one more of these with you and leave you the other two to try on your own. Let's pop down and do this big one at the bottom. We're going to start by breaking down the words. I know ane means single bonds. Pent tells me that we're going to have 5 carbons with single bonds, and the word cyclo means I'm going to put them in a ring. Let's start with that. Let's put 5 carbons in a ring. 1, 2, 3, 4, 5. I'm going to connect these 5 carbons with single bonds. I now need to attach some branches. I can see there's branches because of the YLs. The first branch length is F. F means that it's a 2-carbon long branch. The second branch length would be meth. That's a 1-carbon long branch. I can see that these are going to be at carbons 1 and carbon 3. Now, where is carbon 1 and carbon 3 on a chain? The answer is anywhere you want. We can start counting the carbons on a ring at any point. So I suggest you pick a spot where you have room on your page. Right now, I'm going to decide to call this carbon 1. And I could have picked anywhere at all. On carbon 1, I needed to put a methyl branch. A methyl is 1 carbon long. Now I need to decide where carbon 3 is. If this is carbon 1, then this could be carbon 3, this could be carbon 2, carbon 3, or this could be carbon 2, carbon 3. Which one would we go? Again, it doesn't matter whether you count clockwise or counterclockwise. Pick the direction that gives you space to do what you need to do. I'm going to go in this direction. So if this was carbon 1 of my parent chain, this was carbon 2, this guy becomes carbon 3. He needs a 2-carbon long branch. So 1, 2. Anytime you see a ring structure, it is always automatically your parent chain. Anything branching off the ring structure becomes branches. So this was my 1-methyl, 3-ethyl cyclopentane. Just for practice, we're going to put the hydrogens on, and this time I'm going to put them on in the condensed version. Counting first the bonds to the other carbons, this top carbon has 2 bonds so far and requires 2 hydrogens to get to 4 bonds. As does this carbon. He has 2 bonds so far and requires 2 hydrogens to get to 4 bonds in total. This carbon has 1, 2, 3 bonds so far and requires only 1 hydrogen. This guy requires 2, this one requires 1. This carbon in the branch has only 1 bond to other carbons and will need 3 hydrogens to get to 4. We have 1 more branch to attach hydrogens to. This first carbon has 2 bonds, 1 on either side. It needs 2 hydrogens, and this end carbon needs 3. Count first the bonds to other carbons, then choose to label the hydrogens so that each carbon has 4 bonds. Here are 2 other examples of some alkanes. Just to help us practice, we're going to go through how they were named. This first one has 4 carbons in a straight line. Remember, the hydrogens have nothing to do with the name. They are just there to allow each carbon to have up to 4 bonds. So when I'm coming up with a name, I ignore the hydrogens. 4 carbons is bute, and it's all single bonds, so it will end in the name ane. This is butane, sometimes called N-butane, and the N meaning normal, no branches. And that N isn't something that can be dropped. We don't need to have it there. In the second example, the longest chain I find is 3 carbons. It is propane. There is a 1-carbon branch coming off of the propane. That is my methyl, and it's on carbon 2. This is 2-methylpropane. In both cases, however, you will notice that we're going to have 4 carbons, and if you count, you will find that there are 10 hydrogens. Both cases are C4H10. This is why we had to have a special naming system for organic molecules. You can have the same molecular formula, this being a molecular formula, but different structural formulas and therefore different names. When that happens, we call those isomers. Isomers happen when we have the same amount of carbons and hydrogens, but they actually make different molecules, and therefore they'll have very different properties. Now, alkanes can exist as gases, liquids, or solids. The bigger they are, the harder it is to melt and boil them, so the more likely they are to be solids. Alkanes are found, we get them out of fossil fuels like oil and petroleum. We separate them out by distillation. And if you've ever been down to a place like Regina and you've seen a big plant that looks like this is a plant where they're distilling out the different kinds of alkanes that we get from fossil fuels. Gasoline is an example of an alkane that has 8 carbons in it. Often it's called octane, but in reality it is one of the methyl heptane branches. What I'm hoping that you guys can do so far is understand what makes a molecule organic, the fact that it contains carbon, that you recognize alkanes have all single bonds, and that you can name and draw them. We definitely need to be able to practice this quite a bit.